All right, next one is x times ln of x. That's more or less the same as the first problem. Same exact analysis. I'm going to skip that one. I'll move on to number three, which is the integral of x squared e to the 3x with respect to x. Now here, let's do the same exact analysis again. We have a product, which means we should be thinking reverse chain rule, and then parts. We don't have a quotient, so we don't have to think about quotients yet. Reverse chain rule means the derivative of something must be in the problem. The derivative of x squared is 2x. Well, I cannot turn this into a 2x, so that's not going to work. And if we try e to the 3x, the derivative of e to the 3x will be e to the 3x times 3. And there's no way to convert x squared into that. So that's not a candidate. Then we can say parts. Okay, parts, you can always use laity, but before we do laity, and I forgot to mention this in the previous video, always ask yourself, is it of the easy form? Easy form is x to the n sine x, or sine of some easy function, x to the n times cosine of an easy function, or x to the n times an exponential to an easy function. And in fact, this is exactly this form. So this is where the tabular method can be used. And in the previous problem, the tabular method could not be used because it was not in any of these forms. So if you can, try to use the tabular method first because it's going to go much faster. Although that being said, if you can use the tabular method, you can always use just standard UDV parts. So the tabular method says I'm going to make a column for the sine, I'm going to make a column for the derivative, and I'm going to make a column for the integral. Oops, for the integral. I don't know if I need this much space, but it's there. So I'm going to start with plus x squared, and I'm going to integrate e to the 3, oops, e to the 3x. So I'm going to find all my derivatives first, so then I know how many integrals and how many sines I need. Derivative of x squared is 2x, derivative of 2x is 2, derivative of 2 is 0. And then the reason, again, we stop here is because derivative of 0 would just be 0. So this would just be a bunch of zeros all the way down. The moment we hit the first 0, we can stop. So I need sines to here, and I need integrals to here. So I go plus, minus. And now I need to take the integral of e to the 3x. Sometimes people say, well, is it 3e, oops, is it 3e to the 3x, or is it e to the 3x over 3? And the answer is always take the derivative. Check to see for yourself. If I were to take the derivative of this guy, I would get 3 times ln of e, ln of the base, which is just 1, times the exponential, times the derivative of the power. Well, this is not that, so this is not going to be the answer. Now let's try the other guy. Let's verify by finding the derivative. Derivative of this would be 1/3 times e to the 3x times the derivative of the power, which is 3. The 3's cancel. That means that's the correct antiderivative. So this would be e to the 3x over 3. And here is where you can actually start exploiting the pattern. The next integral will be another e to the 3x over 3. But there's already a 3 on the bottom. So this is going to be e to the 3x over 9. And then the next one would be e to the 3x over 9 times 3, which is 27. And if you're not sure, pause the video, find the derivative of e to the 3x over 9, and see that you do indeed get this guy. Then pause the video again, find the derivative of e to the 3x over 27, and see that you do indeed get this guy. And hopefully you have done that. Now we can just write down our answer using parts, the tabular method shortcut. So we can say by the tabular method, the integral of x squared e to the 3x with respect to x is, you go side to side, and then you go down. side to side, down, side to side, down. So positive x squared times e to the 3x over 3 minus 2x times e to the 3x over 9. Positive or plus 2 times e to the 3x over 27. And then had we gone one more step, 0 times whatever would have been there, e to the 3x over 81, well, that 0 starts knocking away all the integrals in the future. So this is our answer plus the almighty constant. So this is an example of how you could use the tabular method. Now, had you done just UDV parts, you'd have to do two integration by parts to get the same answer. That's why the tabular method is considered a shortcut for these questions.